Okay, time for a discussion about ionization energy. This is a new thing that's totally related to all of these ions because this has to do with how ions are formed. In some cases, you're going to be losing electrons. And so the definition of an ionization energy, given this symbol E sub I, it's the energy required to remove the highest energy electron from an isolated neutral atom in the gaseous state. That's a strict definition, but that's helpful when you come back to it on occasion to realize where it derives. From a neutral atom, you'll take away one electron to make it into a cation. So the simplest possibility then would be for the hydrogen atom to become a hydrogen ion, and the value here is given in kilojoules per mole. It's energy required. Energy has to be added to pull away an electron from the gaseous neutral atom. And so on the right you see a separated electron just depicted in a different place from the hydrogen ion that results. Now, this is just simple hydrogen. Let's see what else we can compare. So if you take this chart of ionization energies compared to atomic numbers, there's some great clear periodicity in this data. The maximum values on each of these are always in the noble gases on the top of each peak. As you go across a period, the ionization energy is greatest for the noble gases and smallest for the alkaline earth metals. Well, think about it. If you're going to pull away an electron from an atom, the noble gases are going to be unlikely to lose electrons, which means those ionization energy values are going to be very high. They're very stable, so they're not likely to lose an electron. They're stable, full noble gas can figure full electron shells. And by comparison, the alkali metals only have one in an outer shell, and taking away one is going to be not nearly as difficult because it's farther away from the nucleus for the number of protons that it has. So it will give you the minima at all the alkaline earth metals. Nice pattern to notice. Now, there's some other curiosities in ionization energies that are worth noting. The group 2A elements are going to occur as a slight bump, if you will, as you progress across a period. So we're looking at beryllium or magnesium or calcium and their corresponding periods. And so the ionization energy of beryllium is a little bit higher than boron, and magnesium is a little bit higher than aluminum, but in a general sense it still increases as you go across a period. Not entirely without some variation here. So the beryllium has a larger first ionization energy than its neighbor boron because it's removing the first electron from a 2s orbital. It is a filled orbital. And so taking something away from a filled orbital is going to be require more energy than taking away an electron from the next orbital, the first p electron for boron. Similarly, aluminum is going to be a little lower than magnesium for its first ionization energy because you're pulling away an electron from a 3p orbital, and magnesium you're taking away from a filled 3s orbital. So it has also to do with the effective nuclear charge. In other words, the charge of beryllium is +4, and you're pulling against electrons of 4, and boron you're pulling of electrons of 5, but 5, the boron has a slightly lower ionization energy because you're shielded by the 2 inner shell electrons of the 2s subshell that are not shielding the electrons of beryllium. So it's a little bit more shielded, more easily removed. Now, look at the other side of the chart. Group 6A elements, such as oxygen and sulfur, have a little bit of an anomaly as well. Oh, back up. I'm going to finish talking about the beryllium and the boron example. So here's the actual values. Nobody's needing to memorize numbers. There is a difference in the values of ionization energies, but beryllium is losing an electron from a filled 2s subshell, and you're losing from a single occupant 2p subshell in the case of boron. The shielding on the boron amounts to the outer electron being shielded from the charge of the nucleus of the 5 protons in the nucleus of boron by 4 electrons. And so that is more shielded than the 4 protons of beryllium being pulling against outer electrons, but there's only 2 inner electrons. And so the effective nuclear charge is a little bit larger there for beryllium. Gives you a larger ionization energy to pull away that first electron. So 2 different effects contribute there. Okay, now let's talk more about the oxygen anomaly, oxygen and sulfur bump, if you will, in the curve or pattern, the graph. As you progress across the periods, oxygen and sulfur both have some slightly higher, or slightly smaller, excuse me, so I said it backwards, value than their neighbor if you were progressing across the atomic numbers. So why is that? They have slightly smaller than expected because the first electron is removed from a filled orbital. A filled orbital is going to have 2 electrons in it, one of each of opposite spins. Let's look at that in more detail and see if that makes sense. So if we're looking at nitrogen, the first electron being, the ionization energy corresponds to taking away an electron from a singly occupied 2p orbital. So, oops, I should have made the line with breaks in it. Okay, so let's make boxes. And so boxes for the 2p subshells might be like that. And the half-filled orbital will have 1 electron each. So you're pulling away 1 electron from that configuration. But in the case of oxygen, you're going to have the 3 2p orbitals with 1, 2, 3, and 4 electrons. So now the last electron, the first electron removed, is going to be taken away from a filled orbital. One of the set of the 2p orbitals is going to lose an electron, and you'll end up with a half-filled orbital instead, but it doesn't take quite as much energy to take one away from there because the electrons repel one another, and so it's more favorable to pull away electrons that are in the same ones from a pair in a filled orbital because they have some repulsions. The taking away from a half-filled orbital is somewhat a little bit more stable and a little more difficult to remove. So that gives you an explanation for the patterns where oxygen is a little bit lower than nitrogen, and sulfur is not too much different than phosphorus, but doesn't increase as much as the corresponding ones in the same way. Okay, so let's keep generalization going here for our ionization energy, so we need to remember what we're looking for. So the ionization energy is going to increase in a period with increasing atomic number, which is what this general chart shows us across each period, generally speaking, but of course there's some zigzags in here that we've mentioned a little bit. And but when you have a filled first shell at helium, it's going to be the maximum. Filled second shell with neon, it's going to be a maximum first ionization energy. Argon, again, has a filled third shell, maximum ionization energy for that period. And krypton, it's got a filled fourth shell, and xenon, a filled fifth shell. So increasing in a period with a 2 atomic number. Now, make sure you remember the pattern. The alkali metals are going to be the lowest and highest for the noble gases. The noble gases are very stable. It takes a lot more energy to lose an electron, a lot more than their neighboring alkali metals. So keeping this pattern in terms of the actual periodic table instead of a graph that shows periodicity, what do we want to remember? So increasing ionization energy occurs at the top of any period because there are fewer shells, and that makes a big difference in how the electrons are held. So fewer shells means that you have greater energy required, fewer electron shells, greater energy required to remove the electrons than when they're farther away in the bottom of the period. What else? What other patterns do we need to remember? The ionization energy increases as you go across a period, and so for any one period it's always increasing, going to the right. But in another point to notice is that the metals are going to have relatively lower ionization energies than nonmetals because they tend to lose electrons much more readily than nonmetals. In any case, that is why they form cations, and the anions are from nonmetals. Within a group, so the ionization energy is going to decrease with increasing atomic number. Within a group, it's going to be decreased lowest at the bottom of the period. Now, again, the anomalies have to do with things like magnesium and aluminum, which has aluminum is a little bit more shielded, and the aluminum is going to be a little bit lower than its neighbor magnesium, just like the beryllium and boron example. So it's got a little more shielding, and it's a little easier to pull away an electron than the first one for magnesium. And whoops, wait on this one. And in group 5A and 6A, paired electrons in the group 6A result in more repulsion, and those are easier to remove. So the 6A ones are going to be a little bit lower because they're repelling their paired electrons in that p orbital are a little easier to remove than the first electron from the neighbors in group 5. Repulsions makes it easier to move electrons. Okay, that would be enough of the discussion for ionization energy for the moment.